And now, welcome to this session.
This session explores the transformation of Java source code into bytecode, detailing the compilation process, and how bytecode enables Java's efficiency and portability across different platforms. We have with us another duo for our next presentation, both software developers at IBM. Ashwin, a recent graduate and former IEEE technical coordinator, is part of the IBM WebSphere team. His co-speaker, Virata, is a contributor to OpenJDK on AIX. She's also a recent Technical Collaboration Achievement Program Award recipient. Together, they will unveil the secrets from Java source code to bytecode. Give a round of emojis to Mr. Ashwin MS and Ms. Virata M.
So, hi everyone, a very warm good morning to each and every one of you. So, I hope my audio is clear and you don't face any difficulty. If yes, please just put in the chat. Okay, I think we are good to go. So, our topic is that Java source code to bytecode. Excellent. So, let's see what exactly is bytecode, what is so special about it, and why Java bytecode is so useful. So let's say Java as a language is platform independent, right? So it is given the tag write once and run everywhere. Like how it has got the tag write once and run everywhere and this platform independence tag. But Java has also JVM. JVM is platform dependent. Why? Because JVM converts the bytecode generated by the Java compiler to a machine language. The machine language, as the name suggests, it's a OS dependent. So it becomes platform dependent. So this bytecode generated by the Java compiler makes the Java platform independent and gives the status platform independence or write once run everywhere. They're actually universal and they're also known as portable code, peak code, and also intermediate language for the VM to execute. Yeah. So bytecode, as I said, is contains a lot of instructions that a machine can interpret, and also there are many languages, many number of tools that make use of bytecode. So bytecode is basically can be is used in Scala, programming languages Scala, JRuby, Groovy, and of course Java. Java has Java C, and these languages have their own instruction and they compile with their own compiler to generate the bytecode. And mostly this bytecode is more related to JVM than Java as a language because it is described its instructions and everything in the JVM specification, not on the Java specification. Let's move on and see behind the scenes of um, what happens, like how it's generated and how we get the output. So we have the source code that is .java and it is compiled by the Java C compiler and we get .class file, which of course is a bytecode. And we use a Java P tool to view this disassembled code. And then this .class file that contains the bytecode is then loaded into JVM by using a class loading scheme, and the JVM will interpret because it has a Java interpreter dynamically and links together and gives the output, the required output. So JVM is actually a stack-based VM. That is, each functionality is passed to the stack in JVM. So it is actually related to reverse polished notation. What exactly is reverse polished notation means? Let's see an example. That is sum of 1 comma 2. How it is treated? 1 plus 2 is equal to 3. Whereas in reverse Polish notation, it will be taken as 1, 2 plus. So initially they will push 1 to the stack, then it will push the next argument 2 to the stack, then it will call the sum function and we get the output 3 and it pops the 3. That's how it works. So yeah, moving on, we can see how what kind of bytecode instructions are there, how it is categorized. So there are a few of them that I listed, right? Stack manipulation, method invocation, synchronization, control flow, math and exceptions and returns. So basically we will cover a few of them in details and few of them will be covered along with the example that will be discussed towards the end of this session. So the stack manipulation basically talks about how we load and unload the value onto the stack when a function is called. When the execution is completed, this whole stack is collapsed and destroyed. And on method invocation, we talks about how the method is invoked. So we, for example, we can take a system.out.println of some string. In that case, it how it is passed to the stack and how it is invoked. So it is actually takes the println, then the out, then the system, and then pass the some string. So basically, everything on source code is read from left to right, whereas on bytecode we take it as in backwards. Then we talk about synchronization. We will deal with the bytecode instructions for synchronized methods or blocks, and then we have control flow. In control flow, we talked about the bytecode instructions for all kinds of jumps and ifs, and we have math and then exceptions and returns. Moving on, let's talk each one of them. Yeah, before that, let's just see what is stack frame. So in a thread, there will be dedicated stack frame which contains operand stack, constant pool, and local variables. What this operand stack is for? We will load and unload a value when a function is called. Then we have local variables, store and retrieve the local variables of a program. Then we have constant pool. Constant pool actually holds the constant values of a program. Here comes my next question actually. How exactly a method name is stored onto the stack? When a method name is invoked, how it is stored onto the stack? What if the method name is too big? What if it is test threshold dot Java or something more big or uh, method name? In that case, we have constant pool comes to our rescue. That is, we actually store the actual method implementation within the constant pool and we give them a particular index. And when a method is invoked, this index is being called to the operand stack. That's how it's done. So moving on, let's see stack manipulation. Next slide, please. Yeah. So stack manipulation, there are many kinds of operations, stack operations, or we can say stack in instructions. As you can see, we will discuss few of them with an example. And yeah, let's go. See, you can see the initial stack which contains two elements, n1 and n2. And on the left hand side, you can see the operations swap, overdub, to dub, drop, and clear. These left hand side instructions are called opcodes or mnemonics. This makes the bytecode instructions human readable. So initially it performs swap operation, that is, it swaps the first element with the second. Then over operation, it actually copies the second elements to the top of the stack. And dub operation actually duplicates the first element. And coming on to the next slide, yeah. Thank you, Ashwin. So there is two dub. It actually copies the first two elements and duplicates the first two elements, sorry, and yeah, put it on the stack. Then we have drop operation. It will pop the first element from the top of the stack. Then we have clear operation. It will empty the stack. So there are other operations also like tuck and depth. Tuck actually copies the second element and put it on the first element and put it on below the second item. And there is depth operation which returns the length of the stack, like how many elements are there in the stack. There are different kinds of operations. So as you can see, you may have noticed there were two different kind of dub operation. One is dub and one is do dub. So on dup operation, what we do is duplicate the first element. On two dup operation, what we do is duplicate the first two elements, right? When we are duplicating the first two elements, we put those two elements in the two stack cell instead of putting it in the one stack cell. Why we are doing this, and why not we are not putting it in the same stack cell? Because it is a single operation, but we use two stack cells, right? Why it's like that? So basically, if we are invoking a program and it contains int, mostly the whole stack will be of size 4 bytes, that is int. And if we passing a double value, in that case it will take space of two ints, that is two stack cells. Yeah. Moving on, we have stack instructions. So there are two kinds of instruction, that is load and store. Basically, it's read and write operations, and instructions change depends on the JVM type. So it actually, if it's a object or a reference, then the prefix will be a. And on JVM, we know that how many primitive data types is there. So 9. And also that is, sorry, 8 primitive data types and one object or reference, right? For the object, the prefix will be A. And on JVM, for all the short data types like byte, short, and int, the prefix will be I. As you can see on the table, it will be iconst, iload, and istore, increment, ia load, similar like that, I add. If you want to convert from int to byte, then it will be I2B, or into short, it will be I2S, and similarly for float, long, and double. Yeah, moving on. Then we have method invocations. Method invocation basically, as I said in the constant pool, when we need to invoke a method, it loads the method index from the constant pool onto the stack. So JVM basically have um, four kinds of invoke instruction, that is invoke static, invoke virtual, invoke special, invoke interface. And on Java 7 they also introduced invoke dynamic. So on invoke static, they basically invokes a static method. So when the JVM sees an invoke static instruction, what exactly they do is, okay, they need to call the static method. That's what JVM is instructing, right? And also static method basically links to a class, not an object. So we don't need to pass instance as an argument. For example, we can see some math.square root function or integer.value of functions. These are all static methods. So whenever these functions be needed to be called, the bytecode instruction will be invoke static. Then we have invoke virtual. Invoke virtual is instruction in JVM is used to invoke a virtual method. So virtual method is nothing. Basically, it is any method that can be overridden in subclasses. Okay, so this also supports polymorphism, and method that needed to be invoked in case of virtual method, it's determined by during the runtime, whereas in case of static method to be invoked is determined at the compile time. And if we need to invoke a virtual method from the constant pool, it is done via virtual dispatch. So basically, when JVM encounters this invoke virtual instruction, it has an index. This instruction will have an index, and it will go to the constant pool of class file, which contains the method name and the reference. And method index is basically nothing. It is an offset of a virtual table of compile class time. And virtual table is just an array where each entry is pointing to actual method implementation of the targeted method. So JVM will return the runtime type of the object. So basically, when this particular method, virtual method invocation is done in the same manner for several iterations, what JVM does is the JVM will record this kind of behavior, and it will avoid going to the long process, and it will directly go and get the cache target method. In that case, it increase the performance. That process is actually called inline caching. They also will check like assertion check, because JVM should know when this particular thing is failing, because this is of same manner. Virtual invocation was of same manner, right? When it becomes different, it should know, and this particular check will fail. That is, it basically check the runtime type of the object. If it is not same, in that case, JVM will redo everything from the start. Moving on, then we will talk about the invoke special method invocation instruction. That is basically when a JVM sees this instruction, that is invoke special, JVM will know exact place to look into the V table in order to get that requested method. So this is considered in the three cases. That is, one is private methods, then calls to superclass methods, and calls to constructor body. And then we have invoke interface. Invoke interface instruction is used by the JVM to invoke a method on interfaces. There will be multiple classes that will be using the same interface, right? That is, it supports polymorphism. When a call is happen to invoke a particular method, in that case, JVM will know which dynamically will and automatically will figures out like which particular class implementation is needed to be invoked. Then we have invoke dynamic. Invoke dynamic, before talking about that, Java, is a static and strongly typed programming language. With invoke dynamic feature, JVM can dynamically link the correct method at runtime, and that is a particular feature introduced on Java 7. So, for example, we can take an example that is a function a plus b. We don't know the type of a and b at compile time. With invoke dynamic, it directly links to the correct method at runtime based on its type. So yeah, this is the one main use case of invoke dynamic. Whenever invoke dynamic instruction is executed by the JVM, it directly calls a special static method called bootstrap method. So bootstrap method is nothing. It is just a piece of Java code to set the logic to get the correct method to be invoked. That is the actual method. So whenever this bootstrap method is invoked, in that time, it will go to the call side. Call side is nothing. It returns a reference to the actual method. It is also known as method handle. Next slide, please. Okay, let's see. We have seen few of the method invocation and JVM instructions for that. So let's see with an example. So you can see on the left hand side is the program, and right hand side is a piece of bytecode. Note the whole bytecode for the program. It is only for the main method. So as you can see on the index 0, what it is doing, invoke static, and you can see a hash 25, right? Hash 25 is nothing. It is telling that on constant pool at index 25, we will get this static method. It calls the static method, which doesn't take any, you can see on the brackets, there is no, nothing is passed. That is, no arguments is being passed, and it returns void. That's why we. Then you can see on the code what it's doing in the main. On main, you can see method invocation demo dot static method. That's why it invoked the static method. On the next line on the program, you can see method invocation demo is equal to new method invocation demo. What it is doing is creating a new object, right? So on 3 to 7, it creates a new object with new, and on index number 6, it duplicates it's on the stack. On 7, it calls the invoke special, that is the constructor. You can see the constructor public method invocation demo on the program. Then it stores the object on local variable 1. On then a load 1, it then loads the reference from the local variable 1. Then again it calls the invoke virtual instance method. That is explained by the programming language demo.instance method. Similarly, when animal dog is equal to new dog, line is explained from line number 15 to 19. It creates the object, then it duplicates it on the stack, then it calls the invoke special. Why invoke special? Because it's a constructor. Then again, it stores it into the local variable 2, then it loads the reference from the local variable 2. On index 24, you can see invoke interface, and at 37, that is why interface animal, you can see it is an interface and calls the sound dog.sound. That's what it's happening. Then it calls the invoke dynamic. So invoke dynamic is basically implemented for the features like Java records, string concatenation, and lambda expression. As you can see, runnable R equals system out dot println invoke dynamic triggered is actually calling a lambda expression. Here, invoke dynamic, what it does is the runnable object is linked to the lambda expression is invoked, and it is then calls a bootstrap method with run that links it to the run. So a store of 3, then it loads stores that object into the local variable 3, and a load 3, then it loads the reference from local variable 3, and then it calls the invoke interface, that is runnable.run. So it calls the run method from the runnable interface. That's why it is a invoke interface, and it returns. So that's all about the method invocation. So let's pass it to Ashwin, and let's dig a much more about bytecode with few interesting examples. Yeah. Over to you, Ashwin.
Thank you, Varada. So we have been looking at some of the topics that we had been initially be referring to from the beginning. So we'll see what we have to talk about synchronization is, and then we'll move on to some examples. So you just to make sure that everybody knows what synchronization is, you all might already be familiar with it. This is when an object is can be accessed by only one thread at a time. That is, it is something that should not be accessed by many threads at one single time. Before we actually talk about how synchronization works, we just need to familiarize ourselves with the ordinary object pointer. This is a pointer to an object, and it contains mainly two fields. The first is a mark word, and then there is a class pointer. The mark word actually consists of a certain identity hash and the garbage collection age and some other synchronization information, that is lock and the monitor. That is what we are actually going to be looking into detail. And then there is the class pointer, which points to the class information about of this object. It tells about the static fields and the v-table for method invocation. Okay, so how does this thread acquire a lock? So let's say a thread is entering into a synchronized block or a method. It can be anything. So it needs a lock on this synchronized block before actually doing anything with it, to make sure that no other thread is accessing it. A lock can actually be biased towards a method. Let's say there is thread 1 and there is thread 2. So let's say thread 1 is the one which actually needs this synchronized block the most and uses it most of the time. So a lock can be biased towards this thread also, so that it can reduce a lot of operations. And when a thread is actually owning a lock, the mark field is updated to show this bias. So let's talk about what this biased locking is. So let's just take thread 1 and thread 2, and there is a synchronized block. So thread 1 needs to use this synchronized block for most of the time. So what this does is that when the lock is actually biased, it optimizes performance by avoiding a lot of atomic operations. Like there is a compare and swap operations that is done based on how many threads try to access a synchronized block at a time. So when you know that thread 1 needs a lock the most, we can avoid a lot of compare and swap operations. Along with this, a question might arise. So what if one thread actually wants to acquire a lock? That is actually possible, that when a new thread comes up, the bias lock can actually be reversed so that the new thread can acquire this synchronized block. Okay, now we have been talking about this lock a bit. Let's see like what kind of states can the lock be in. The first thing is a neutral state. That is, no thread is holding the lock. The synchronized block is unlocked and ready to be used by any thread. And then is the biased state. That is what we have been talking mostly. It can be locked and unlocked, and it is at an unshared status. That is, only one thread is accessing this synchronized block at a time. Sorry about that. So a single thread has locked this object up, and the lock is biased towards this thread. And as we talked before, a lot of compare and swap operations can be avoided here. And then there is the stack lock state. What this means is that a thread is locked and it can be shared, but it's like uncontended. Like there are not many threads that are like trying to access this synchronized block right now. The mark word will point to the the stack of the thread that is actually holding the lock at the moment. And in order to actually lock or unlock this for other upcoming threads, you need to do some compare and swap operations. The next state is the inflated state. in this state, the synchronized block is locked, it's shared, and it is contented, which means unlike the stack lock state, the thing is that there are other threads trying to access this right now, and one thread is actually holding the lock while the other threads are queued up for getting the access. And the markword points to a heavyweight object monitor structure, which actually stores info about these threads that are in the queue. Okay. These are like two bytecodes that we need to familiarize ourselves so that we can actually understand synchronized blocks a little bit more. The first one is monitor enter. The thing is that when a thread actually attempts to get the lock, it attempts to gain the monitor. That is a reference at the top of the operand stack. And there is an entry count field. If the entry count is 0, it means that the thread can actually enter the monitor, that it can acquire the lock. And once it enters the monitor, it increments this entry count so that it knows that, okay, something has gained access of this synchronized block. Let's say if a thread already owns the monitor, it can re-enter the monitor by incrementing the count again. That is when there are two methods inside a static block or anything. Let's say method 1 and 2 is there inside a certain synchronized block. And the thread entered the first method. When it enters the second method, which is inside the synchronized block, it will increment the count again. So there in the 0 will actually be converted to 2 once the thread actually enters the second method. And if another thread owns the monitor, the current thread blocks until the monitor is free, so that no other thread can actually access the synchronized block. Then there is the monitor exit, which is the exact opposite of enter. What this does is that exactly opposite of what we saw before, it decrements the entry count. So let's say it was 2 is changed to 1, and when the first method is also exited, that 1 is turned to 0. So when the entry count reaches 0, the monitor is actually released and the synchronized block can be taken up by any other thread. Okay, so we have been talking about bytecode for a long time. So we can actually take a look into how it actually looks like, what all stuff you can see there, the type of instructions. Like if you are someone who has used machine assembly language and everything, this will seem very familiar to you, but there are some differences. Like we can get to see that in the following examples. Some of you might already be familiar with the Java P utility. So Java P is the utility that allows you to disassemble the class files. Let's say you have a class file and you have using the Java P utility, you can actually display your bytecode and see what is going on inside. And the thing is, Java P has a lot of options that you can do, much similar to many other terminal commands. You can use the -c, -v options and everything. We'll look into that in the coming slide. So based on the option, you can alter the kind of output that you see. And this output that you get from Java P is printed to std out. That is, if you are taking it from the terminal, it will be shown on the terminal screen itself. Let's say if you want to store it somewhere, you can actually pipe the output to a text file or any other type of file of your choice. And one very nice feature about Java P is that it is backwards compatible. So you can use the latest version of Java P and disassemble classes that were compiled by an older version of it. So that is like a very good feature of Java P. And the syntax for this is Java P followed by options followed by the class files you want to actually disassemble. You can give multiple class files to the single Java P command and actually see what's going on. It doesn't limit you that way. Okay, what options are available for Java P? So there are like a lot of options. So the first thing is no option at all. Like what happens if you simply use Java P for a class file? So what this does is that it prints you the package information, the protected and public fields. It just shows that and not much of the bytecode. You can use the help option to show that every option that is possible. So it shows you a small instruction set on. It's basically like the manual command. So the thing is, it shows you what all options you can use, and based on your need, you can find which one is suitable for you. And the version option shows you the release information, so you can check what version of Java P is on. If you want to know whether you are on the latest version, you can use this. Two very important options you can use are -c and -v. So let's see -c first. What this does is that it prints the instructions that the bytecode is comprised of. So like the bytecode that we have been talking about till now, you can see that by using the C option. If you use the V option, it prints the stack size, the number of local arguments, local variables and arguments for the method for which the bytecode is being shown. So that is the difference between C and V. If you use the V option, you get the same output as C along with the some extra information. And these are some of the few handpicked options. You can use the help option to actually see what all options are available to you. Okay, so we had talked about math and control flow instructions. So now we can actually start looking into the bytecode and see how this works. So we have a small demo function over here. It is pretty straightforward. There are two integer variables, num and I, and num is being initialized to 15, and there is a loop, and this loop will iterate 10 times and add 1 to num every time the loop is iterating. So towards the end, this will be 25. So we can see how the bytecode looks like. So towards the right side, you can actually see the bytecode. For the simplicity, we have shown the bytecode of this exact method only and not of the class. Okay, so as we explain this further, you can actually see the highlighted line, and that's what we'll be dealing with every slide. This is the information that is stack, locals, and argument size. This is the information that you get when you use the Java P minus V option. You won't see this if you use minus C. So what this does is that, what this shows us is that stack size is 2, local array size of 3, and argument size is 1. One might wonder, like, there are no arguments passed to this demo method. So could anyone guess, like, what could actually be the argument 1 here? That there is one argument. Could you, like, guess what it is? The argument here we are talking about is this pointer. So the thing is that once this method is actually started functioning, the thing is that this pointer is actually pushed to the local, yes, the receiver object. That's it, Girish. Thank you. We have a response in the chat. So that is why the argument size is 1. And this happens for all virtual methods. Okay, and the local size is 3 and stack is 2. The reason why local size is 3 is because this pointer, that is a reference, is actually taken into the local array. The stack is 2 because that is all the size we need for handling the operations inside this one method. And this is what the local array would look like in the beginning. Okay, the first instruction over here is byte push 15. That is byte integer push. What this does is that it takes a single byte value of an integer and pushes it onto the stack. But something you need to have in your mind is that even though this byte 15 takes only 1 byte, the thing is it is represented in 32 bits. So on the stack, one slot is actually 32 bits. That is 4 bytes. And the same goes for the local array also. So one slot on the stack is 4 bytes. So let's keep that in mind. So what this instruction basically did is it took the operand 15 and pushed it onto the top of the stack. And this is followed by the I store 1. So it is a pretty straightforward instruction. The I stands for integer, and it is storing a value on the top of the stack to the first position on the local array. Just reminding you that in the local array, we'll be dealing with indexes starting from 0. So 0 is this pointer, and in the first position, now we have the value 15. And this is followed by I const 0. What this does is that it pushes the value of 0 onto the top of the stack. Okay, now this might raise a question in your mind. Why use I const 0? Why not use by push 0? Like initially we had used by push for 15. Why not just simply use the same thing again? So the thing is that, and for every data type, for values ranging in a small range, that is 0 to 5 and all, we have instructions that directly do it. So you don't actually have to give up an operand for that. This makes it easier to actually, it makes the size a little bit lesser for the instruction. So that is why the Java C compiler uses the iconst 0 instruction here. And the next step is storing this 0 onto the local array second position. And now the stack is empty. All the variables needed have been initialized onto the local array. Okay, and this is where the actual fun starts, where we are actually getting into the loop. So first, what happens here is that the second element, that is 0, that was on the local array, has been pushed onto the stack. So that this is basically the first part of the loop. Initially, we have to check whether the loop can actually start. So this is what is going to happen over here. And by push 10. So you probably might be guessing right now. So what is happening here is that we have 0 and we have 10 on the stack. So something is going to happen for the loop. So let's see what exactly is going to happen. The next instruction is the if integer compare greater than equal to. What this does is that it takes the top two operands from the stack. That is 0 and 10 in our current situation. And what this does is that it compares whether 0 is greater than or equal to 10. The format that is followed here is that the first operand will actually be the element that was popped second from the stack. That is 0. Like when you pop element from this stack right now, the first thing that's going to come out is 10. So we do that comparison, and if that comparison is satisfied, it goes to the address 21. That is the return. But in this case, 0 is less than 10. So you don't actually have to jump. So we're moving on to the instruction in line 11. And that is iload1. What happened here is that you can see that 0 and 10 just disappear altogether. And now iload1 pushed 15 onto the stack. What happened here is this, what happened here is that the if instruction over here actually clears these elements from the stack and does not push it back. It does not give another input. Once the comparison is done, you can either jump to the operand value there, or you can move on to the next instruction. And iconst1 pushes 1 onto the stack, and this is similar to the iconst0 operation. The next instruction, iadd, what it does is that it takes the top two operands, adds them together, and then pushes that value onto the stack. So 15 plus 1 equals 16. And this is the part where the num equals num plus 1 instruction actually took place. So you can see how the value of num was incremented over here. And after that, what happens is the 15 value is actually stored to the first operation. So the num value is updated, and now you can reflect it on the local array. And this is what happened over here. And this is followed by the I increase 2, 1. What this does is that it is definitely an integer increase. The first I in the instruction is pretty evident of that. What this does is that it takes this, the first operand as a position on the local array and adds the second operand to that value. So the second value that was 0 was added by 1 over here. And the next instruction is go to 5, and that is we are going to the beginning of the loop again. So you can see that the loop variable I was added, incremented over here. That is the I++ line in the actual method, and we can see what happens next. And the thing is, this 1 is then again loaded onto the stack, and every other operation will be repeated. Okay, so skipping towards the end of that method, what happens is that at some point, the value of I will be 10 and the value of num will be 25. So let's consider a state where I became 10 and we are checking again that whether the loop should continue or not. So we'll see how that works. What happens is 10 is pushed onto the top of the stack, and then again by push 10 is being done. Just notice that the first 10 was the value of I. The second 10 is actually the constant that we gave in the method. And this is followed by the if operation, which clears out the stack and finds out that 10 is equal to 10. So that condition is satisfied over here. So it jumps to the instruction 21, that is the return. So this actually ends this method. Now let's consider the same thing, but using a double variable as the iteration for the loop. So what happens over here is that you can see in the method, instead of an int I, we are using a double I. And the code, the bytecode has actually become a little bit bigger. So you can notice that we have more lines this time. And let's actually get on to how this works. Before we look at the instructions, we have to note that the size of the local array and the stack has changed. So the thing you need to notice about the local array this time is that double data type is something that takes up more space. You need 64 bits. So initially there's a this pointer. The next position in the slot in the local array is taken up by the num. And the thing is, double I takes up 2 slots on the local array. That is why the local array has been increased to a size of 3 this time, and not 4 instead of 3 like the last method that we saw. Okay, now actually we'll see what's the difference with the last method. You can see that most of the instructions over here have a D in front of them. that shows that these instructions are catered for a double data type. Initially, Varada had talked about a few instructions that for every data type, we have certain instructions which help us actually take care of these things. So the first dconst, dstore, deload2, they're all pretty much the same functionality that we talked before. The only difference is that they deal with this double data type. And the thing to notice here is that we have a DCMPG, that is double compare greater than operation. Sorry, it's not greater than, it's comparing only, which is followed by the if greater than 24. You can see that the instruction is actually split up over here instead of a one simple if DCMPG instruction, unlike the integer data type. So what happened here is that double is a more complex data type. It takes more size. So in order to make things easier, it has been split up. So there is no one single double compare instruction that does something for us. The difference here is that unlike the integer compare operation, after the comparison is actually done, the DCMP command, what it does is that it pushes a value onto the top of the stack. It can be 1, 0, or -1 based on the whether it is greater, equal, or less than. And you can use an if operation, that is if greater than or equal to, which takes up that pushed value on the top of the stack and does that comparison. Okay, and this is what actually what the local stack would look like once we start working on it. And we have just taken a reference as two double values being on top of the stack, let's say for DCMPG. And the thing is that each double value takes up 2 slots on the stack. And there is one more thing you can see over here, that is the LDC2W instruction with the #7 as the operand, and it has a comment double 10.0D. So we'll actually talk about that in the upcoming slides. And this is where constant pool loading comes up. The thing is, we just saw that the value 10 is double, so it takes up a much larger size. So before we talk about constant pool loading, we just need to consider these two sizes, that is the 32-bit data and the 64-bit data. So you have the constant pool with a lot of values. It can have integer values, double values, all data types. It can have method names or other strings or anything you have. Okay, the first size is the 32-bit. We can see how this works. You have the LDC command. What it does is that it lets you load 32-bit data onto the stack. But the thing is, LDC command has a certain restriction. You can say a constraint even. Well, the problem is that it can take only a smaller set of addresses, that is 0 to 25. And that is why LDC is used. And in order to tackle that, we have the LDC wide. That is, let's say the constant pool is quite big and you have a lot of data. And let's say a certain constant that you want to acquire has a wider address, more than 255. So you can use the LDC W instruction. Just keep in mind that these two instructions actually handle 32-bit data itself. And the second category is for 64-bit data. But unlike the size 32-bit, you only have one instruction over here, that is LDC2W. This will handle wider instruction set and take up 64-bit data onto the stack. Okay, now actually we can see how this pool, what happens when you want to actually load something from the constant pool. You have a certain function over here. This only has initializations. You can see that int million is a very big value, and double D 1000 is 1000, and long L1 is actually a very big value too. And if you look at the highlighted instructions over here, the first one is LDC #7. So what this does is that it goes to the constant pool, takes the value at 7, and it loads it onto the top of the stack. You can see a comment over there that was actually not written there by us. The thing is, Java-C compiler actually puts it over there so that it is easier to debug the actual instruction. So you don't have to worry about going back to the constant pool and finding out which variable is in which position. And followed by this, following this is the LDC2W. You can see two values over there, and they're taking constant pool operands of 8 and 10. One thing you might have noticed here is that we don't have the LDCW instruction over here. The reason is that we don't like for this small method, we don't really have a very big constant port. So the thing is, you don't exactly need the LDCW instruction here at all. So the compiler just gives us the LDC instruction. Passing arguments onto a method. Now, this is something that you might be waiting to see. You can see that there is a subtraction operation over here with two arguments, A and B. And it is simply returning the A minus B value. And we have the bytecode towards the right. The thing is that any argument is treated as a local variable. So the thing is, once A and B is defined as the method arguments, once this method starts, A and B is actually copied to the local array along with this pointer. This method, like the ones we've seen before, is also virtual. So that's why this pointer is over here. And you can see that locals is equal to 3 because these methods are being treated as local variables. And let's just see what happens over here. Okay. What these two instructions do over here is that we are taking the values from the local array and pushing it onto the stack. So initially, what was pushed was A, and the next one was B. So almost like the if operation that we saw before, and the add operation also we saw. The thing here is that we need to do A minus B. So what happens here is A was pushed initially, and B was pushed afterwards. And this is followed by the I sub instruction. What I sub does is that much similar to the I add instruction. It takes the top two values from the stack, and what it does is that the second element to be popped out from the stack is treated as the first operand, and the first element to be popped out of the stack is treated as the second operand, and the subtracted value is pushed onto the top of the stack. That is about passing arguments. And we have reached the end of our discussion. So before we end, we just want to say that like learning bytecode like actually lets you know how the JVM works, how the code is compiled, and what happens behind all these method invocations, object creation, and how memory is being managed, how that stack size was decided, how the local array size was decided, everything. And this will let you debug your programs a little bit easier. It can be challenging to understand this basically. If you are someone who has used assembly language before, this will be a little bit more easier for you. But even then, with a little bit of effort, it is something that can be very interesting to learn. It will help you debug your programs and understand your programs a little bit more. And this will definitely prove to be a powerful tool for optimizing performance and having an understanding of how these Java programs execute. So we hope you enjoyed the session. Yeah, so we see a lot of questions over here. So Varda, like, can we we'll pick some up and we'll see. Like my chat is towards the end right now. I see a question over here? Like, shall I take this one? Yeah. There is can Java bytecode be decompiled back to the original source? Yeah, the thing is, you have tools right now that will let you do this. Like you can actually decompile the source code, sorry, the bytecode. The thing is that once that is done, a certain parts of the program that might not be actually be there. Like you won't exactly see the exact source code that you provided. Let's say you gave two variables in the program, and let's say one variable is not exactly initialized anywhere. You won't see this initialization in that decompiled source code. So stuff like that can happen. And next, yeah, Varada, you can.
Yeah, so I could see the first question that what are the common errors encountered during the compilation of Java source code? So there will be logical errors. So there will be class not found exception, null pointer exception. If array is indexed out of bounds, then there is an exception. So those kinds of exceptions will be thrown. So before jumping to the bytecode, we could actually fix those and compile again. So we will get the exact bytecode of the source code. So I could also see another question, that is, how does the Java virtual machine optimize the bytecode execution, and what implication does this have for performance? So before that, I could say, so this JVM, inside JVM, we have also defined this about compilers and also about the garbage collection. So for on OpenJ9 VM, I would talk about that. So similarly, there is same for hotspot VM as well. So when it comes to garbage collection, if our application wants higher pause time or application wants less pause time, so we can select the garbage collector accordingly and we can optimize accordingly. So that way, then we have JIT compiler. I also talked about um, inline caching, right? It does the same process. So JVM will definitely stores the process of doing the invoking a method or something, and it won't redo the same from the start and saves the performance, like improves the performance. If there is some assertion failure, in that case only they will redo everything from the start. So that is the 2 points I want to talk there. Then I also see one of them, that is, in what ways can bytecode affect the portability of the Java application across different platforms? So what is Java platform? So Java platform is nothing. It is Java runtime environment which contains Java APIs and JVM, right? So Java platform, it contains JVM. So we will have a JVM for each and every platform. It is put it under the above the OS. It can be treated that way. So if you have a platform, then it for Unix, then it will be for AIX, or it will be for Linux, PPC. As you try to download Java from Oracle site or Adoption site, you will select the architecture and OS, right? That's how you download it. This bytecode is in bytecode generated by the Java C is then put it into the JVM. JVM interprets it, which contains the Java interpreters and gives the loads into the OS. So it is also like it goes like this. It's OS, we have JVM generated bytecode. So it's like a 3 level. You can consider it that way. Mm. So what are the common pitfalls for development standpoint? Should QA team should be aware when testing a Java applications after the compilation process? You would like to take that up? I think it is the same exceptions and errors that we are getting while compiling. Yeah, sure.
Just adding upon what Varada said, like if you have like environment issues, like for example, let's say production and testing environments, like if there are some say differences between them, you can face some issues like that. And like the thing is, you need to be like very exact about like how many threads will be accessing one source something at some moment. Like you face some issues of deadlock or improper synchronization, stuff like that, and you have chance of memory leaks also. Like, but then again, like it's not something that you have to like worry about a lot. So just I just wanted to add upon what Varada had mentioned.
All right, thank you, Ashwin. So the next question is from Kim John. So the question is, how does the Java compiler optimize source
Yeah,
code
I also see
during
one
the
more question that I could
transformation?
answer. That is, are there any subtle differences between how bytecode is executed in Oracle's JVM versus OpenJDK or other JVM? So we could say OpenJDK has hotspot VM, and I would take another example, that is IBM's Semeru has OpenJ9. So the difference is all definitely there, right? That's why they're allowing to create as this copyright and this new JVMs and all those. So J9 is actually having the different garbage collector, whereas for hotspot we have a different garbage collector. Hotspot, it is C1, C2, and on JVM we have opt throughput, opta pause, and gencon and no GC. So there are differences according to the different architectures and different JVMs and all those.
All right, thank you, Varada. So the next question is from Diane May. So the question is, how does bytecode enhance the portability of applications across different platforms?
Okay, so the thing is like we had actually like talked a little bit about this. The thing is that we said like the bytecode as such is the only thing that is portable in like over here, like based on the Java virtual machine that you have, or like on the machine that you're working on. it will be different. So the thing is like this bytecode will actually let you do like run the same class, or like get let's say you want to run a class, then I made a class and I want to give it over to Varada. So the thing is like as long as she has a virtual machine that is made for her own machine, she can use my bytecode which was made on another machine. So that is always possible, and that is the main standpoint of the Java bytecode situation, and why it is platform independent over here. I hope that answers the question.
All right, thank you, Ashwin. So the next question is also from Diane. So the question is, how do you see the role of bytecode evolving in the future of software development?
Uh, just something that had to be mentioned over here is that new bytecodes are not exactly brought into the specification, like into the instruction sets a lot very frequently. The thing is that we have the name itself suggests that bytecode, we have one byte. So that actually gives us a restriction on the number of instructions that we can actually make. The only flexibility is when adding operands. So so I think that you are asking maybe like will there be new bytecodes coming up in the future? Like that will be like very not very frequent. So the thing is that it's kind of restricted. Like everything is done with the existing set of bytecodes itself. Like new instructions are very rarely added.
All right. So Ashwin and
Some of
Varada,
them
would you
have
like
asked
to
about the
choose?
learning path and resources. I
Ashwin?
would say for the learning path, start writing small piece of Java code and compile with the Java P and along with minus C, you will get the disassembled code. In that time, you can understand how it exactly works. And also, there are resources available online as well. I will also recommend reading books like Java Virtual Machine Specification, and also there is one more thing, one more book inside Java 2 virtual machine, the book I have followed through to understand more about the inside works of JVM. So you can follow those two. Yeah.
All right. Thank you, Varada. So would you like to choose the next question, or would you like me to be the one to choose the next question? Uh, would you like me to proceed to reading the next question,
We are
Ashwin and
just
Varada?
looking at the list of questions. Like if there are some common ones, maybe we can pick that up.
Sure.
There is one question over here, like does bytecode prevent the reverse engineering of your application? The thing is that in a very basic sense, like not going into too much detail, like we actually talked about this as an answer to a different question. You can actually see the source code from if you have a certain bytecode with you. But then again, that is only when you actually give us just a class file to someone, and it, like based on your needs, you can actually have ways to prevent this. But essentially, if you have a bytecode with you, you can actually see the source code. But then again, that will not be the exact same thing. Like the decompilers that we have right now, like they might they just simply give you what this bytecode can actually be seen as a source code. And let's say there was some line in the actual program that was not um, transferred over to the bytecode, you might not be able to see that. I hope that answers the question. We just saw this question: which component of Java responsible for compiling Java? Like that is, I mean, we have the Java C compiler. Like I don't know if we are like whether like looking into more detail about it. We just saw the question over there and decided to talk about that. Oh my God. I think like pretty much we have covered almost everything. So Is there anything else?
I think that is all, or would you like to go over the questions once again? I think there's also new entries. But if
Yeah.
you're all right with the questions, we can proceed naman.
Yeah, like I think we have covered almost everything.
All right. Thank you once again, Ashwin and Varada. So, now in case if you still guys have a question for our speakers, you may reach out to them via chat here in the Air Meet. So that's all the time that we have this for this session. So if you enjoyed this session, please give your rating and share your feedback about our speakers. You'll find the link in the chat box. So again, let's thank Ashwin and Varada by clicking those emojis. Send your hearts, send your claps. All right, I see many claps here. Thank you so much, guys. So you may now exit this session and click on the next. Bye, guys.
Thank you all.
Thank you, everyone.